Hello, and welcome back to CS33 Introduction to Data Structures and Algorithms Part 2, and we are now on our Module 9, and this is the last module for the SEM, so kaya yan, ito na yung last module natin, and we will be discussing about greedy algorithms. We have 5 videos for this module. The first video is for the introduction to greedy algorithm, and again, I will be giving a simple example. The example is the coin changing problem. Okay, and then succeeding videos will be more examples. We will be providing a greedy algorithm for the single source shortest path problem, which is yung Dijkstra's algorithm. We will be emphasizing the key components of this algorithms for these problems, like the properties and characteristics of the problem. Kaya okay lang gamitin ng greedy algorithm for these problems. And then we will also give a greedy algorithm for the coding problem using Huffman coding. And then we will solve the minimum spanning tree using Prim's and Kruskal's algorithm. And yung greedy algorithm, hindi lang siya nagwo-work for easy problems but for hard problems as well. So, hindi nga lang optimal yung sagot, but for this module, we will be sharing that we can use a greedy algorithm for solving a hard problem. And that example will be the traveling salesman problem. Okay. So greedy algorithms use the greedy technique. This technique is only applicable to optimization problems or those problems that have an objective function where we try to either minimize or to maximize. So for instance, we are already familiar with TSP. So TSP is an optimization problem where our objective function is the total distance of the tour and we wanted to minimize the total distance. So that is an example of a minimization problem. And then the knapsack problem is also an optimization problem where we try to maximize the total value. Okay, so yung greedy technique, it only applies to optimization problems like TSP and knapsack problem, because it utilizes the idea of an objective function. Okay? Before we discuss some properties of the greedy technique, let's look deeper dun sa idea ng search problem. Okay? So, if for an optimization problem, we either get the optimal solution if we can get to a global maximum if it's a maximization problem, or if it's a minimization problem, we can get to a global minimum. Okay? So, for the exhaustive search, you can enumerate all possible solutions. Okay? So, for knapsack problem, for example, we have 2 to the n possible subset of the n items. And for that case, we can search through all possible solutions and we can output something that has the global maximum or the highest value. However, not all the time we have the capacity, both with respect to time and computational capability to explore all possible solutions. So what we can do is sometimes we limit the search space to just a portion. That's one way of reducing the time complexity, but of course we cannot guarantee that we can get the global maximum. Okay, so again, going back to the definition of the greedy technique, it is applicable to optimization problems. Okay, and we construct a solution for an optimization problem piece by piece through a sequence of choices. So, kumbaga, binubuo natin yung solution natin, papira-piraso, and making sure that it will satisfy the constraint, so it's still a feasible solution. Pangalawa, it's locally optimal, meaning for all the possible choices, siya yung pinaka-best bet. So, that's the piece na magko-contribute to best bet. And then, it's irrevocable. So, as we try to construct the solution, yung nagawa natin in the previous time step, hindi na natin pwedeng mabawi. Kumbaga parang naging part na siya ng solution. Okay? So, again, the greedy technique constructs a solution to an optimization problem. Okay? So, paisa-isa, piece by piece, through a sequence of choices that makes the solution feasible. The way how we select a piece is by locally optimal choice. And pag naglabas tayo ng piece, hindi na siya pwedeng mabago pa. To give you an idea how pieces of the solution is obtained, let's try to look at the two problems again. So let's start with the knapsack problem. So the definition of the knapsack problem can be described using the input and output. Okay, so for the input, you have a set of n items, that's from 1 to n. Tapos, you have an output which is a subset of the n items. This subset can, for example, if this is an optimal solution, this will provide the maximum value. Okay, so when we say pieces of solution, ang isang piece dito is an item I. So, kumbaga, for the greedy solution, we are trying to create something like this that can include item I. So, pwede tayong magdagdag ng item, and that's how we do it. So, that's the greedy algorithm, creating a solution piece by piece. So, we can either add item per item to the solution. Another example is the traveling salesman problem. Okay, so again, for the description of the problem, we have the input and we have the output. For the input, we have a graph with vertices and edges, and we have weights. So suppose this is a complete graph. And a tour can be represented as a sequence of permutation going back to the first position. So since this is a complete graph, for example, we can have a tour na 1, 2, 3, 4, 1. And the pieces here are the path. So path from 1 to 2, path from 2 to 3, and so on, hanggang sa makabuo tayo ng buong tour. So that's how you complete a solution piece by piece, or that's how you construct a solution piece by piece. Okay. So, the manner how we will include pieces is via the description a while ago that is locally optimal. So, we can add 1, 2 because 1, 2 has the lowest weight among all the possible path that emerges from 1. Okay, so as I described a while ago, when we try to show you something like this, a graph with a global maximum and a local maximum, hindi lahat ng problems have this kind of structure when you try to exhaust all possible solutions. Some problems are easier, and yung types ng problems na yon are called convex problems. So, imagine if you have graph that looks like this, where each x coordinate here is a feasible solution. If you try to provide a greedy algorithm for this, your local optimal solution is the global optimal solution. However, if you have something like this, okay, ganito yung itsura ng search space niya, then you can have a local minima and a global minima. Okay? So, for some problems, this greedy technique yields a global optimal solution just like this one. For most, it does not, but can be useful for fast approximation algorithms. So parang, instead of producing this one as the output, this one is a good enough solution for the problem. So there are, of course, problems that have optimal solutions using greedy strategy. The first and the simplest example is the change-making problem for normal coin denominations. Later on, I'll explain the definition of a normal coin denomination. Okay? The second example is the minimum spanning tree. And we also have the single source shortest path, simple scheduling problems, and then Huffman codes, which will be discussed in the succeeding videos. And then I'll explain one case wherein the greedy solution is not the optimal solution for the problem. So in this case, we have the traveling salesman problem, and what we will provide in the last video for this lecture is a greedy technique for the traveling salesman problem. So this solution is called an approximate solution for the traveling salesman problem. So it's also the running time of the greedy strategy is always linear or polynomial time. So mabilis lang mag-run yung mga greedy algorithms natin. But if you can provide a polynomial time solution for problems that are hard, then nag-collapse na yung PC ko 20. So, ganun yung para implication nun. So, usually, ginagamit yung greedy strategy for problems that are hard to provide an approximate solution for the problem. Okay, so for our first example, it's called the change-making problem. So I am showing here a denomination set. So we have V1, first denomination, which is 10 pesos. Second denomination, 5 peso, 25 cents, 10 cents, and then 5 cents. Okay, so this is called a normal denomination because we can arbitrarily specify, let's say, for Bangko Sentral, actually, gusto ko ng 12 pesos na buo. I can have 7 pesos and so on. So that's an abnormal coin denomination. So most of the countries have this set of denominations. And it's so good because the greedy algorithm for the change-making problem only works for the normal denomination. So let's try to look at one example with a normal coin denomination. So we have d sub 1 to d sub m, where generally we can have m denominations. In this example, we only have 6 denominations. That's from 10 pesos to 5 cents. And then another input is an integer. Okay. Hindi lang pala necessary integer, no? Kasi we can also have in cents, no? So we also have a number, a real number na 25. Hindi nga. Kailangan ng ata. It's a real number. Suppose we have an integer that is n, and that n is 25 pesos. Okay, so suppose magpapabarya ako, I have 25 pesos, pabarya nga po. The output should be the coins that can represent 25 such that the total number of coins is minimum. So the output is represented by C sub 1 up to C sub m, where each C sub I is the cardinality of the coins. Okay, so one example is the worst possible barya given 25 pesos. I can hand 500 pieces of 5 cents. Okay? That is equivalent to 25 pesos. So that's the worst possible because I have 500 coins equivalent to 25 pesos. Let's give another example that is way better than our previous example. So suppose we try to arrange the denomination from the highest to the lowest, and we'll try to provide coins nakakasya dun sa highest denomination and so on. Okay, so let's try to construct the solution by providing C1, C2, and so on. Okay, so for initially we can start with 25 pesos. We can have 2 10 peso coins, so that is 2 times 10, so I have 20, and then we have a remaining 5. For the next denomination, which is 5 pesos, I can have 1 coin, so that's 1. Okay, so the final answer, since wala na tayong natira from the 25 pesos, is a total of 3 coins, 2 for the 10 or the first denomination and 1 for the second denomination. So again, we tried to construct the final solution by identifying the pieces of the solution starting from the highest denomination hanggang sa lower denominations. Okay, so by using this greedy algorithm or greedy technique for this problem, we obtained the least possible coins that is feasible. So we only used 3 coins instead of, let's say, 500 doon sa worst case scenario natin kanina. Okay? So that is an example of a greedy technique for the change making problem. And in reality, this problem actually have an optimal substructure property. So remember that in the optimal substructure property, you can use the optimal solution for the lower or for the smaller instances. In this case, our smaller instance is yung natira na coins. So we have a smaller value for this one, and then natitira na lang yung for the next denomination na smaller. So we can use that optimal substructure for the greedy algorithm. However, hindi lahat ng greedy algorithm with an optimal substructure, hindi lahat ng may optimal substructure has an overlapping subproblems. And in this case, if we have a normal coin denomination, it is proven that the greedy algorithm is an optimal solution for this problem. If we have an abnormal coin denomination or unconventional coin denomination, then it has an optimal substructure and it also has an overlapping subproblem. So we can use the dynamic programming to solve this problem optimally.